Like I was saying last time, we defined the difference between average rates of change and instantaneous rates of change. So the limit as dx approach or delta x approaches zero of x plus delta x minus f of x all over delta x. Um, this is the limit definition of a derivative. Okay. And so we had two different concepts. One was this idea of average rate of change, which was this notion of a secant line, right? I told you about the secant line, correct?
Yeah.
Yep. So secant line slope equals average rate of change, AROC. And basically what happens is if you bring these points, the 2 points you see here, we'll call it x equals A, x equals B. And if you shrink these points closer and closer to each other, right, and bring them so close together that they're effectively, so they're infinitesimally close to each other, right? And then you end up doing the secant line, or the slope between those 2 points, and effectively you get this thing known as a tangent line. And the tangent line, those 2 points are, since they're infinitesimally close, you're taking the limit as that delta x between the 2 points approaches zero, so you're effectively at the same point. So this is the way we define this thing called the instantaneous rates of change. Rate of change and tangent line. So this is tangent line. Okay. And you remember intermediate value theorem, what it said?
Yeah. So if you have 2 points like x is equal to a and x is equal to b, like
Mm-hmm.
in a function that's graphed,
Yep.
um, for any value c in between a and b,
Mm-hmm.
for the x value, you'll have a value L that's in between f of a and f of b.
Right. Yes. And you will have some x value that gives you that same L value as the
Yeah.
output. Yeah.
Yeah.
Yeah. The only thing you got to make sure you say in that definition is make sure the function's continuous. Okay.
Okay.
If the function's not continuous, then it doesn't hold true. So if x equals a, x equals b, um, then we have some f of a.
Wait, why does it have to be continuous?
So if it's not continuous, there's nothing guaranteeing there to be some. So, for example, that's a good question. Let me just draw a separate diagram.
Mm-hmm.
Okay, so if it's not continuous, if you have like a piece that goes like this, right, and it just stops here,
Yeah.
and then the function starts again over here, right? Intermediate value theorem says that, so let's say this is x equals a, and this is x equals b,
Okay.
right?
Yeah, I get it.
You
Yeah.
know what happens, yeah. So
Yeah.
if f of a is less than f of b, so you know that there's going to be some L in the interval a to in the interval f of a to f of b, right?
Mm-hmm.
So there's some L that you can choose. There's an infinite number of L's, right, in between that. And there is some X value in the interval A to B, right, which gives you that L value. correct? So any
Mm-hmm.
L value you pick, there must be some X value that produces that L value if the function is continuous. Okay, if it's not continuous, then, of course, if I pick some L value here, then there's no X value defining that.
Yeah.
Yeah, so,
Mm-hmm.
of course. Okay, that's good. Yeah, nice. Okay, so, yeah, so that was sort of like a quick review of what we did
Yeah.
last time. Um, yeah, so now I just want to get some notation straightened out. So derivative. Okay, so the derivative notation, there's like many different ways you can write the same thing. Um, One of the ways, the most common way you see in math, there's actually two, which is the Leibniz notation, which is if you have a function f of x, um, I believe this is the Leibniz notation, and this would be df dx would represent um, the derivative of f. Okay, and you can also say um, so let's write derivative. And this is the same as saying f prime of x. Okay. These two are the most common ones that you see. You will see another notation later on if you're differentiating with respect to time. So, are you familiar what that means, differentiating with respect to time?
No.
Okay, it
It's,
just means that. So, notice how I'm doing df dx, right? So,
yeah.
x is the independent variable.
Yeah.
Um, if I have a function that's in time, right, f of t, so x, the independent variable, is time. And if I'm differentiating that, df dt is the way I would represent that, right? Um, it's the same as saying um, f dot. Okay? When you see a dot on top, that just means it's the time derivative of f. Okay? If you
Uh,
see two dots, that just means it's the second derivative, and so on. Yeah. And again, we haven't talked about the second derivative and those things yet, but just know that this is the notation we will be using. Okay. Um,
mhm.
yes, estimating derivatives of function at a point. Okay. Let me get some logistics to sort it out. Second. Okay. So if you want to ever find, now you understood the idea of, defining this instantaneous rate of change. Um, so what does that mean? That means, let's say I have a car moving, with, so x is its position, okay? Or, yeah, position, and we have time, okay? So if, let's say, the position is going something like this, okay? So um, if I take the derivative of this graph, or x of t, right? If I take the derivative, what does that actually represent?
The velocity.
Yes. So v of t equals x prime of t, right? Or you can say x dot. Um, and the thing you should know is if I ask you for your velocity at a specific time, what does that mean? It's like saying
Instantaneous velocity.
instantaneous rate of change or
Uh,
velocity at a given time, right?
yeah.
So if your car is traveling according to this path, right? This x path, it's going really fast here, it slows down, picks up the speed here, keeps going, right? Um, and if I ask you to define the speed of the car at a specific time, it's like saying I find its velocity function by differentiating, right? I
Hmm.
differentiate and I get velocity. And then I evaluate velocity at a specific time. So some t1, let's say. And that's velocity at a specific time. Um, or it's the same as saying derivative um, of a function at a specific time t1. Okay? Um, and of course, if I ask you, your independent variable can be anything you want it to be, right? So if I just ask you to evaluate the derivative at a specific point, the process is you take your function, you differentiate it, and then plug in that point that I ask you to find the derivative at that point. Okay,
Hmm.
it's quite straightforward. Um, okay. Now, we talked about continuity when we did limits, right? So we have what's your definition of continuity?
It's continuity. It's like continuous.
Yes, but what does it mean though? Like sound like a mathematician when you say it.
There's no like jumps or like
So
there's no jump like your graph like there's no jumps or anything. It's
right, I know you can visualize it in your mind, and you're
yeah.
just struggling to say it, but the way to do the way you should define continuity is if you have some interval of x, right, from a to b,
Yeah.
every single x value has a definite y value, right? It's
Mm-hmm.
defined for every x value in that interval. That's the definition of
Yeah.
continuous. Um, and of course, you can have continuous. Well, here's the thing: you can't have functions which are um, like let's say, this doesn't count as continuous. Okay, because although I have a defined, so imagine a piecewise function, right? So it's some y equals some constant c here, and y equals some other constant here, right? Notice how it's defined. So this is x. X is going this way, okay? So it's defined for every x value all over here, and then it goes over here. And then now what happens? There's a jump discontinuity, right?
Mm-hmm.
So this does not count as continuous. You cannot evaluate the derivative at points like this, okay? You're because think about what it would mean. What are you actually doing when you're evaluating a derivative? You're saying if I want the derivative at this point, you pick some point that's like infinitesimally close to it, right? To the right, and then you find the line that connects the two.
But that doesn't like
That doesn't
exist.
exist,
Yeah.
right?
Okay.
Because of this jump here. So, which is why you can't really do the derivative at these sorts of jumps. And of course, I think that goes without saying. If you have something like this, a whole, and then continues, you
Yeah.
can't
Yeah.
evaluate it here. Yeah. So that's what I mean by connecting differentiability and continuity. So continuity and differentiability. Now, there's one more thing. Differentiability implies continuity. Does that make sense?
Um.
This implies continuity. It's just
Oh yeah,
saying
yeah,
if
that makes sense.
something's
Yeah, yeah,
differentiable,
yeah.
you know it's
It's
continuous,
continuous. Yeah.
but not the other way around.
Yeah.
Because this does not imply differentiability. Because of another case I'm about to tell you. So, of course, I told you you cannot evaluate derivatives when this happens, when you have jump discontinuities or holes or anything, right? But the other thing is when you have something sharp like this, okay, like an absolute value function, for example, you cannot differentiate it, okay? So when you have like a sharp peak, as they call it, sharp peaks, um, and or cusps. And cusps are something that looks like that or something, okay? Or, you know, like this. This is a cusp. Something like this, yeah. Okay? You cannot evaluate derivatives at sharp peaks or cusps, as well as jumps, jump discontinuities, point discontinuities, etc. Right? So that's why this statement makes sense, right? Is this
Mm-hmm.
function continuous everywhere? Again, if this the interval,
Yes.
yes, but it's not differentiable. So
Mm-hmm.
if it's differentiable, then that implies continuity, but continuity does not imply differentiability because you can have a continuous function that's not differentiable. Okay? And the most famous example is absolute value of x. Okay?
Yeah.
At least it's not differentiable at x equals 0. You can, of course, differentiate absolute value x elsewhere because then it's just a line, right?
Mm-hmm.
But you know what I mean.
Yeah.
Okay. And one more thing I should mention is you could have a cusp, a like I don't know, like a jump discontinuity, and then it's just well behaved after that. Okay. Now, if something like this happens, it's not differentiable at this point, but it's differentiable everywhere else. Okay. So sometimes your function, you could represent it sort of as a piecewise function. So you could differentiate just this piece up to this point separately. You could differentiate this piece separately, and from here to infinity separately. Does that make sense? So you have
Wait, does that also apply for like the other types of discontinuities, like where there's just a line and it's away from it's not like near like for example, you know the example you showed
Mhm.
where there was a jump discontinuity?
Yes, yes, yeah,
Like, yeah, so can you still differentiate in like the other sections?
yes, of course.
Yeah.
Yeah, you can everywhere other than
Yeah,
this
okay.
point. Yeah, you
Yeah,
can differentiate here because it makes perfect sense, right?
yeah, it
Like,
does. Yeah,
yeah, yeah,
yeah,
yeah.
it's
That's why it's just a slope of 0. Yep.
yeah.
So again, you got to be very careful. Usually, when they give you problems, they give you functions that are differentiable. But if you have asymptotes and like a bunch of crazy stuff going on, you got to be careful. Okay. Now, with asymptotes, on the other hand, um, you could just say like if the derivative's extremely high. So okay, what happens with an asymptote? Let's look at that. That's something worth looking at. Asymptote and differentiation. Okay, so if you have something like some vertical asymptote here, let's say, and this function sort of like starts doing something like that. Now it's not actually getting to a vertical line, right? Because then that would mean it's not a function.
Yeah.
but it's not it's like almost a vertical line, but it's just not. Its slope is incredibly high
Yeah.
as it approaches. Okay, so if its slope is extremely high, we just call this what do we call that? It's just infinite slope, right? Because for every change in y, if you just think of what the derivative is, it's delta y over delta x, where delta x, the limit, is being pushed to zero, right? Um, Now, if uh, if you approach an asymptote, what's actually happening? You're getting steeper, right? So that means for every change in y, you have a smaller and smaller change for x, right?
Yeah.
And what does that mean? It means if you evaluate the derivative closer and closer to the asymptote, it's just going to keep getting larger and larger, right? So that's why we say the derivative is effectively infinite. Okay?
Hmm.
And of course negative infinity here. Right?
Yeah.
Any questions on that?
If your asymptote was at x is equal to 0, then it would be would it be defined because when you're doing your limit, like your x is like 0, right? So or
Um all right. Can you give me a scenario of what you're trying to refer to?
like it's literally like the same thing you drew. It's just
Yeah.
translated left, so the asymptote to x is equal to 0.
Yeah,
Like yeah.
let me do that. Okay, and then what's your question?
So does that still like change anything? Like the
Yeah,
derivative?
it's the same, right? I mean,
Okay.
like you can't if you get if you try to evaluate the derivative closer and closer to zero, it's effectively infinite. There's no point of asking what's the derivative at some point near zero, right? You can just say it diverges.
Okay.
Yeah. Yeah, that's good. And you will see this if you actually like find that. So we can actually do it, right? What is that function? That's um,
Rational.
what's that function? Yeah, I know it's rational, but is it like
It's 1 over x.
oh yeah, 1 over x. Okay, so now if I want to differentiate 1 over x, and we know it has an asymptote at 0, right?
Mm-hmm.
Because it's undefined there. So let's see what happens. Um, I'm just going to do the derivative quickly. Um, or actually, this is a good practice for you. Try using the limit definition of a derivative. Uh, so this is the formula. And do this for 1 over x equals fx.
All right.
Yeah, and now after that, what I want you to do is once you find f prime, right, you find the derivative. Um, so plug in values that are close to zero from the negative direction and the positive direction and evaluate a few derivatives and see what happens. Okay?
Mm-hmm. Yeah, I mean, as your x values keep increasing or decreasing, I mean, your your y values decrease.
Um, so did you plug in values that are close to zero, like in the derivative?
No, I should probably do that.
Yeah, do that. What did you get for your derivative, by the way?
A negative 1 over x squared.
Yeah, that's right. Yeah, so now all I want you to do is plug in like x equals negative point 001, negative point 0001, and maybe point 001, point 0001. Plug in these and evaluate what the derivative is at those points. Yeah.
Right. Yeah, so for negative 0.01, I got negative 1 million, and then it
Yeah,
just keeps getting bigger as you
right.
go smaller,
Exactly.
like
So
negative 1.
effectively, what we say is the derivative is just diverging at zero.
Yeah.
So it goes to negative or positive infinity. Okay.
Hmm.
Um, okay. Good. Um, 1 second. Oh, going back to notation, I should probably give you one more type of notation. You know how at y equals f of x, right? You can also say y prime. Okay. Y prime is the same as df dx, or you can do dy dx, which is very famous. Okay,
Hmm.
it's all the same. Um, okay, so now I'm gonna teach you the first shortcut for how to do the. I think you already know the shortcut for a derivative of basic polynomials, just the power rule.
Oh yeah,
Um,
that one.
just to review, if you have something of the form x to the n, dxn. Oh, by the way, you can also write it like this. If you have some function f of x equals x to the nth, right? And you want to do f prime of x is just equal to d dx of x to the n. Okay? It's the same thing. And when you do that, you get n times x to the n minus 1. So this is known as power rule. Very famous. And next, we can, the differentiation operator is known as what's linear. Okay. And linearity in math is just when you have some operator, okay, and it follows these properties of distribution. So if you have dx of f of x plus g of x, let's say, okay, it's just of course carries forward and you get f prime plus g prime, okay?
Yeah, so you can distribute like normally.
Yes, it's a linear operator. So this is
Mhm.
if you can do this, if you can distribute like this, it's something known as a linear operator in math. And the other property of a linear operator is if you have c times f of x and you want to
Mhm.
differentiate that. So some constant times a function is the same as c times f prime of x, which is the same as c times df dx. Okay?
But wait, why the C is still like inside the parentheses though? So why is it like
Um,
not? Why aren't you taking the derivative of C?
because c is a constant, you can just pull it out. Okay?
Oh, okay.
Yeah, so I mean, if you think about it, if I have some constant like y equals 5, okay,
Hmm.
y prime is just 0. The reason is you could just use the power rule because
Yeah, yeah.
it's just 5x to the 0. But the other more logical reason is it, slope. Well, differentiation just means slope, right? You're finding a function that tells you the slope at every point, right?
Mm-hmm.
What's the slope of a constant line like this? This is just y
Zero.
equals 0.
Zero.
Yeah. So the derivative is just 0. So there's no point of differentiating it. And if you have something like, let's say, 2x squared plus 4x plus 6, try differentiating this.
Mm,
Use the
four,
power rule and tell me what you get.
four, 4x plus 4.
Right,
Oh, sorry. Yeah, 4x plus 4. Yeah.
right. So you get 4x plus 4. And based on this rule that I just told you, if I pull out some constant, right? And of course, let's say 2 times x squared plus 2x plus 3, right? Now I'm differentiating this. And notice how this thing is like the f of x here, and this c is like the 2, right?
Yeah.
So if I do that, I should get, and I'm claiming that this derivative is the same as 2 times the derivative of x squared plus 2x plus 3. Is that correct?
Mm-hmm.
Yeah. So if these two are equivalent, then this rule applies. Okay? This rule right here.
Oh,
So,
only if those two are equivalent, then.
well, no, it's just like if you have c times some constant, you can just pull out the constant. You don't have to like worry about it. Just pull it out of the derivative and just differentiate the function, and you can multiply the constant out later.
Yeah.
Okay? So if you have something like c times f of x plus c times g of x, and you want to differentiate this whole thing, d
So
dx.
it'd be C D D X. Like you pull the C out. Yeah.
Yeah, so you can just do c times d dx of f of x plus g of x. We're not done yet. And based on the other property, it's just c times df dx plus dg dx. Right?
Mm-hmm. Yeah, you have to like distribute it.
Yes. Does this make sense?
Yeah.
Okay. So, yeah, this is why we call it. So, this is the sum rule. If you have two functions added, you can just use the addition property, which is just this. Actually, you did it without even knowing. You see it right here? This is a separate function by itself. This is a separate function. This is a separate function. And you differentiated it and just added it, right?
Yeah.
Yeah, so that's why this property works. Okay? It's quite straightforward. And the ddx of c times f prime f of x is also quite straightforward. We just showed it here. And now, um, oh, difference. Yeah, if you, of course, I should just say let me just change this to a plus or minus, and this would just become plus or minus. Okay. So if it's a minus, then you would just subtract the individual derivatives. If it's a positive, then you just add. Okay. So in other words, if you have 3x squared minus 5x, and this is g of x, and this is f of x, and I want you to differentiate this whole thing. Okay. You just subtract, right?
Yeah,
Because
so
they're being subtracted.
6x minus 5.
Yeah, so what you effectively just did was g
Yeah, I
prime
did
of
it.
x
Yeah,
minus f prime of x. Yeah.
yeah.
Okay, this is some very basic stuff. All right. Any questions on that? If you practice this, I think you'll get
Yeah,
very
it's fine.
fast. It's
Yeah.
quite easy. Yeah. All right. Derivatives of more exotic functions now. Uh, you may have to try doing. Here, let's see what happens if we do limit definition of a derivative for um, cosine x or sine x. Okay. So we have sine of x plus dx, okay, minus sine of x all over sine of all over x, right? Or is it dx? Yeah, dx.
Yeah.
It is dx, right? Yeah.
Mm-hmm.
Okay. So let me change this to dx. Okay. So how would you evaluate this? I know if you did it with polynomials, I made you do this with polynomials, right? And stuff just cancels out, right? But now you have something like sine to deal with, sine x. So how would we deal with something like this? How do we actually get some derivative out of this limit definition?
Well, we have to use their trig identities,
Correct.
like the
Yes.
sine x plus
Yes.
sine x cosine x plus, I mean, sine x
Yes.
cosine dx. Yeah, we have to do that.
Yeah. So let's do that. Can you tell me which identity we can use? I don't have them memorized, so.
It's been a while, but I think I remember. It's like it's the addition one. Like I forgot what it was exactly called.
Uh,
It's so it would be like sine x cosine times cosine dx, and then plus sine dx cosine x.
Yeah, let me just.
Uh,
I'm just pulling it up to be
yeah.
sure, you know. Yeah, there's gonna be a point where I'm gonna ask you to rememorize them when we get to Calc BC. In BC, you're gonna do something called integration with trig substitution. For that, you need to know how to do trig identities.
Yeah.
But uh, yes, you're right. Okay, so the definition, I'm just going to write the identity. Sine x plus dx is just sine x and then cosine dx.
Mm-hmm.
Okay. And plus cosine x sine dx.
Yeah.
Okay, good.
Mm-hmm.
Uh, Let me make this better. Cosine x sine dx. Okay. Um, and now if I plug this in, I should get sine. Okay, so limit as dx approaches 0 of sine x cosine dx plus cosine x sine dx, cool, minus sine x all over dx. Okay. Um, Now let's see what happens. We
Are you?
get. Sorry.
Oh, I was gonna say, do you like factor out the sine x next? Or-
You don't. Yeah, that's the intuition, but you don't have to do that because you can't do that. First of all, because of there's no sine x in every.
Oh yeah, wait.
But
Oh
the
yeah, my
thing
bad.
is, notice how dx is tending to zero, right?
Yeah.
So if cosine
Oh
of
yeah. So you.
dx tending to zero is just one, right?
Mhm.
So this just turns into one. This turns into zero, right?
Yeah.
So I get uh what do I get? I get sine x minus sine x over uh over now you get a dx. Now what's
Yeah.
the problem with this? There's some problem.
Um, like your dx is approaching zero, so you have like
Yeah,
a zero in the denominator.
and a zero on the top as well.
Yeah. Yeah.
So, this is why the limit definition is not really enough to evaluate these functions, okay? Because you get 0 over 0. And when you get 0 over 0, remember what I told you? You have to do this thing called L'Hopital's rule. But, anyways, we'll get to that later.
Mhm.
So, we need to find a more clever way of differentiating sine, okay? So the easiest way to do it is think of the graph. And I think we'll do this and end it for today. And then next class we'll talk about some more exotic derivatives. Okay, so sine looks something like this. Um, yeah, something like this.
Mhm.
Um, and now its derivative is just its slope at every point, right? Correct?
Yeah.
Okay. So now tell me, is its slope um, is its slope like high over here or low?
It's getting lower and lower.
So it's
Uh,
high. It starts off high and then it gets
yeah, it starts
lower,
off high.
lower, lower. And then what
Yeah.
happens over here? The
And then it be
tangent line is
zero. It's the
zero.
slope zero.
Zero.
Yeah.
Yeah. So at the peak, it's always a slope of zero because the tangent line is just a
Yeah.
horizontal line, right? So let's sketch that out. Okay. So if this is f of x, then f prime of x is just the slope at every point, right? So
Mhm.
at 0, it has a high slope, right?
Yeah.
So you said the slope keeps getting lower. So I'm bringing the slope down, and then you said it hits 0 at exactly this point, right?
Mhm.
And then what happens?
The slope it gets increasingly negative, like
Right,
more negative. Yeah.
right. And it gets more and more negative, and then what?
And then it gets more positive. Like not it like sorry, it gets less negative closer to zero.
Right. Okay.
Yeah.
So with that being said, it gets more and more negative,
Mm-hmm.
and then it must, it becomes um, negative. It stays negative, right, up to this point,
Yeah. Mm-hmm.
and then what happens? It's 0 again, so it
Yeah.
must go back to 0 at this point. Okay,
Mm-hmm.
and then it gets positive again. It's steep.
Yeah.
It increases. Okay,
Until it like hits zero again.
and then it hits a 0 here, and then so on. Okay,
So it's
and then
cosine
it's
x.
cosine. Yeah,
Yeah.
it's just the sine wave phase shifted, so we know this is just cosine. So f prime of x equals cosine of x. This is the graphical way of thinking about it, and I think there's some proof of deriving. Let's see. Looks like I guess there is some way of doing it with limit definition. Okay, so here's what they did in the You have to sort of like rewrite it though. Um, and let's do that real quick. So we had yeah, so we had it correct up to this point, and then they want to rewrite it like so that was sine x minus sine x. Oh, I see. Plus cosine x. Okay. So, do you have this written down, this part?
Oh yeah, I do.
Okay. So just keep that with you. Stare at it. Now I'm just going to rearrange some things, okay?
Mm-hmm.
So it just turns into delta x approaching 0 of uh, sine x times cosine dx minus 1 plus cosine x sine dx. Do you see what I did? So
Just
effectively, if you distribute this out, you still get the sine x cosine dx term, but then this negative sine x that was it was at the end, right? But now
oh,
it's
you
just
got it.
in
Yeah.
between. Okay,
Yeah.
so it's just rewritten over delta x. And now we can do what you said earlier, which is factoring out the sine.
Yeah.
So this turns into limit as delta x approaches 0 of um, oh, I should note that when you have this fraction, you can split it up, right? So you can say um, of sine x times cosine dx minus 1 over delta x, right? Um, plus cosine x sine dx over delta x. We can split this completely legal, right? Into two
Yeah.
fractions. Now, if we just apply the limit to each fraction individually, we get limit. So I'm going to apply it to this fraction and this fraction, but I'm going to pull out some things. So I'm going to pull out the sine x out of the limit. Okay? Because remember, I told you back in
Yeah.
the
Yeah.
day,
You can pull out that const.
it's a
Wait.
constant, right?
Yeah.
Because I'm doing the limit for delta x, not for x.
Mm-hmm.
So sine x is just effectively a constant, sort of.
Yeah.
Okay. Um, so I get cosine dx minus 1 all over delta x as delta x approaches 0. Um, and I'm going to do similarly, I'm going to pull out the cosine x here, okay? And then the limit as delta x approaches 0 of sine x, or sine dx over delta x. Good so far?
Yeah.
Um, and now we get, let's see what happens. Um, okay, so over here, I think even their derivation sort of like fails at some point, anyways. But the idea is this term on top just goes to 0, right? I know technically you're getting to 0 over 0, and that's not the same as just 0. I get it. But imagine I were to tell you that this limit, if you use some more advanced techniques, it just goes to 0, okay? So this limit right here goes to 0 if I were to use this thing known as L'Hopital's rule, but let's ignore that for now. So this goes to 0, so this entire left term goes to 0, right? And again, if I use that same L'Hopital's rule for this limit, I get 1, okay? So then, effectively, I just get cosine x.
Mm-hmm.
And that's why the limit of, or the derivative of sine x is cosine x. And this is a more analytical way of proving the same thing. But graphically, it's easier to see, right? Just it makes perfect sense.
Yeah.
Yeah. So the trig functions are actually very easy to work with because they, it's the differentiating trig functions is easy. They just keep going sine, cosine. However, next class I'll teach you what happens when you differentiate cosine x. It's a bit different, but
I remember it was like negative sine x.
yeah, it goes to negative.
Negative.
I might as well do that now. Okay, so you go through a similar process, but now for cosine x, and you see that cosine x is just negative sine of x. Okay. Um, and again, you differentiate this using the same method or looking at the graph again, and you get. Actually, you don't have to do that. Since you already know the derivative of sine x is cosine x, right? So if I tell you to do derivative of negative sine of x, remember from the constant rule where I can just pull out the constant, right? The c. So there's a negative 1 out front, right? I can just pull that out and say negative 1 times the derivative of sine x,
So
which
that'd be
is just
negative
negative
cosine.
cosine x. Yeah. Again, the same process. I know derivative of cosine x is negative sine x. So if I do derivative of negative cosine x, I can pull out the negative 1, differentiate just the cosine x. I get this right here is just sine negative sine x, right, from here. So
Mm-hmm.
negative 1 times negative sine x is just sine x.
Yeah.
So you see it goes back to sine x.
Yeah.
So it sort of behaves in this like cyclic pattern you can imagine. So sine x goes to cosine x goes to negative sine x goes to negative cosine x goes to sine x.
Mm-hmm.
And each arrow is a derivative, okay? Does that make sense? Each arrow is a derivative.
Yeah.
Okay. So, yeah. So in the next class, I'll go over some other trig functions and how we can derive them from just this and something known as quotient rule and product
Yeah.
rule, etc. Okay.
Alright.
All right. Take care.
Bye. Take
Yeah.
care.
See you.
Mm.